Yeah?
Oh, I thought that was an alarm, and I was like, seriously?
Oh my gosh, I always freak out when they like email us about like the fire drills and stuff. I'm like, just not during calculus.
Sorry, we had one AP Lit once. He was like, no, just continue during your test. Yeah, we're like on the floor. No, excuse me. So everyone took out their phones.
Yeah. Okay. So let me give you a set of conditions. We are going to for Taylor's series, they will tell you how many terms that you need to include. They'll say like fifth order or sixth order, like they'll tell you how many to include. That's a T, sorry, that looks like an O. I'll fix it. Because you guys, what we've been doing, and we're going to do it on the calculator today, is we've been taking like sine and cosine and e to the x and writing them out as polynomials. So when we wrote e to the x was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial and so on, you're taking a function when your calculator finds values for sine and cosine. It's doing it as a polynomial because it can't memorize all of the values for sine and cosine. So what it's doing is for the sines and cosines and ln's and logs, it has stored in there a polynomial approximation for those functions, and then it can evaluate by just plugging x in and doing like regular number crunching, because it's not like it can memorize all of the values, or that you could possibly ever program in every single value that a person would choose to enter. So what we're looking at is taking functions that are not polynomial, sine, cosine, e to the x, ln, stuff like that, and writing them as polynomials. So that's what we're working on doing. So what we're going to look at, they'll give you conditions and they're going to give you values and then derivative values, how to take that information and construct the polynomial for any function that's given. Okay, so I'm going to give you information. We're going to do some quality algebra in the beginning. Okay, so we are constructing a polynomial. So I'm telling you the polynomial at 0 is 1. Oh my gosh, my handwriting's sketchy. We'll make that a 0. My polynomial at 0 is 1. My first derivative value is 2. And these are just generic values. On the AP test, they will tell you the value of the polynomial, the value of the first derivative, the value of the second derivative, the value of the third derivative. So they will give you those. Or they will give you a known function where you can take the derivatives and then generate the polynomial. So either way, they'll either give you the values or you can find these values. So this would be a case where they're giving you the values. Your third derivative is 4, and shocking, I'm going to make your fourth derivative 5 just so that we've got happy numbers. After the third derivative, remember that when they write it with parentheses, it doesn't mean that it's a power, it means that it's the derivative. That's how you indicate higher derivatives. So after the third, like, stop making the little marks because you'll be there forever. Okay. So what we're going to do, guys, is we're going to go back and we're going to use these conditions. We're going to go back and solve for the coefficients. And then we're going to look at the pattern of the coefficients, so then we know how to generate from a given, like they're transcendental functions where they're not polynomials, and rewrite them as polynomials. So we're going to start, we're going to do algebra. If I plug 0 into my polynomial, I can solve for one of the coefficients. So look, if I plug in x equals 0, you can solve for what? and solve for a naught. You guys, if I plug in, I know if I plug in x equals 0, it's supposed to equal 1. So my polynomial is 1. And then if I plug in x equals 0, all of those x's are gone, and you just have a naught. So when you go to take a function and write it out as a polynomial, the first term of the polynomial will be the original function evaluated at whatever point we're talking about. Okay, so now you need to take the derivative. So when I take the derivative of my polynomial and plug in 0, the value is supposed to be 2. Okay, so I'm going to put the 2 equals. I'm going to take my derivative and then plug in 0. So when I take my derivative of a naught, what do I get? 0, because it was a constant, so the derivative is gone. What's the derivative here? A sub 1.
Oh, that makes sense.
Now when I evaluated x equals 0, what can I solve for? Okay, so do you guys see where we're going? So when I now evaluate at x equals 0, so I evaluate at x equals 0, and I now have my a1 is 2. Okay, so I'm going to repeat it one more time and then leave you on the last 2 to finish on your own. So now take your second derivative. So that's why I wrote out the derivative, is so that I had it to keep going. So now take your second derivative. We're going to set it equal to 3 because that's the value they told me to set it equal to.
They're not going to give you the top. Are they going to give you the top piece? Or is it just the generic?
We're going to do the generic, and then I'm going to show you like the general formula. Like this is how you write a Taylor series. Either you find the values of the derivatives, or they give you the values of the derivatives. And then I'll give you a general formula. What's a sub 2?
3.
Okay. So keep going, find a sub 3 and a sub 4. And then I'm going to go back and write it a little bit differently.
Then do we write it all out? Like,
I'm going to go and try to show you the pattern for those coefficients. So then we have like a generic formula. Like this is now, no matter what, the formula that you're going to use.
Okay.
To show you where those coefficients came from. For the a sub 3, so that I can see the pattern better, I'm going to leave my a sub 3 as 4 over 6. Otherwise, it will be difficult for you to see the pattern. I know usually we definitely would reduce, but it's difficult to see the pattern if you reduce this.
Would you change 2 to 2 over 1? Because you have a denominator then, or up in the very first one? You know, like
I
make
will
everything
when I get there. I will.
It goes 1, 2, 3, 4, 5 on the top, and then it goes around the top. Okay, yeah, because then it's 2 times 3, 6 times 4, it's 24. So you have 2 and 1. And then it's 3 over 2, and 2 times 3 is then a denominator of the x, then 6 times 4 is then a denominator of the x.
Yeah. Okay. So you guys, I need you to make sure you can find these values. So now I'm going to plug them. I'm going to write. I asked us to write a polynomial that met these conditions. Okay, so now I'm going to plug them back in. So my polynomial, and I'm going to strategically write some of these, like Maddie asked, should I write it as a fraction? For the 2, should I write it as a 2 over 1? I'm going to so that you can see the pattern a little bit better. So my first term is a 1. My second term is, put 2 over 1, x. My next term is 3 over 2x squared, and then 4 over 6 x cubed, and then 5 over 24 x to the 4th. Okay, so I know you guys, when I was listening to you talk, you see the pattern on the top. Okay, the top goes 1, 2, 3, 4, 5. Where do those come from? Where else did I have 1, 2, 3, 4, 5? Okay, so now you guys,
Gosh, you could have just left it on.
whatever values they're giving you for the derivatives become the values of the numerator. Okay, that's always where they're going to come from. And I'm actually going to put this over 1, and I'm going to write,
And those values multiply together.
this is an x to the 0, and that is an x to the 1. Okay. Denominators.
Oh crap.
We just went back over this yesterday. 1, and then 1, and then 2, and then 6, and then 24. Okay. We just went over yesterday, we went back over factorials yesterday. If you pay attention to like where this 24 came from, my 4 came in front as a 3, and then the 3 came in front to give me the 12, and then the 2 came in front to give me the 24. So I had, up here, I had a 4, then I times it by a 3, then I times it by a 2, then I times it by a 1. So 24 can be rewritten as what factorial?
4.
Okay, so I'm going to rewrite some stuff. So I'm going to leave it the 1. I'm going to rewrite this denominator.
Oh, so would that be 0 factorial and then 1? Oh.
Do you remember yesterday when I read you that
Yes.
ridiculous, it is arbitrarily so that the
Yeah.
formulas work? This is one of the
I went
cases.
and looked it up.
So the formula, I was so like, oh, what? But at any rate, here we go.
Is there a reason you left the 2 on the bottom of that one?
Yeah, because I'm just going to put a factorial with it. Okay, so we just talked about this 24 came from 4 factorial. 6 is what? 3 factorial.
2 factorial.
This is 2 factorial.
1 and then
1 factorial, and
0.
okay, so there was a reason I added in this x to the 0.
2 plus 1.
Okay, so now the generic, like, this is how you make the coefficient. Okay. This 1 came from the 0th derivative, like I don't know how to say it, but like from not the derivative, the original function. The 2 was from the first derivative. This came from the second derivative. This came from the third derivative. This came from the fourth derivative. Like your generic coefficient,
Is the derivative.
the derivative over
The factorial.
the factorial x2.
The derivative.
Okay, so the generic coefficient for how we are going to generate our Taylors, you're just going to have to not ask until I'm like completely done. Okay, the top comes from the derivatives. So the top is, and that's, I talked about the parentheses reminding you that that meant the derivative. This was centered at what x value? Okay, this was centered at x equals 0. And notice these all just had x's, not x minus numbers. So for these, if it is centered at 0, it is your derivative evaluated at 0. Okay, so this was my my fourth derivative over the 4 factorial. So whatever the derivative is, that's the factorial on bottom. Okay, so this was my third derivative over 3 factorial, second derivative over 2 factorial. So this gives me my coefficient, and then the variable piece,
I'm sorry, is that f of n times 0?
it's the nth derivative of n evaluated at 0. So remember, parentheses means that it's the derivative So it's not a power. So like over here, when I did fourth derivative, it was in parentheses to indicate that it was a derivative and not an exponent. So it's the nth derivative of my function, evaluated at 0, over the n factorial. And then your variable piece is x to what power?
N.
The n. Okay, so all of these match. This is specifically at x equals 0. The only thing that will change if I put it to a number is when I evaluate my derivative, instead of plugging in 0, I'll plug in that number. And here, instead of having x, I'll have x minus that number. Okay, so that's the only thing that will change. So this generic formula for how to generate this is when it is centered at x equals 0. They give it a specific name when it is centered at 0, so they don't have to say it's centered at 0. Maclaurin, Taylor generalized it and said, hey, this will work for anything, even if I'm not at 0. Maclaurin developed this method specifically at x equals 0. And then Taylor's like, hey, you know what, I'm pretty sure we can get this to work anywhere if we make slight modifications. Okay, so if they ask you to generate a Maclaurin series and they don't tell you where it's centered, you need to know that it's centered at 0. Like, that's just an assumption that you need to know. Okay, so with that over here, we're going to write the coefficient and the variable if it's not centered at x equals 0. Okay, so if it is centered at some number, so if it's at x equals pi over 2, or if it's at x equals 3, if it's not at x equals 0, you're going to follow all the same steps. My coefficient so the coefficient is still going to be, you're still going to have to do the n derivatives, but instead of plugging in 0, you're going to plug in a. N factorial still has the same. And now instead of just x, you need to have, bless you, x minus. Okay. All of my students remember this. They typically forget it here. Even the answer book, on some of the questions out of the book, they will forget this piece. And my kids freak out, and I'm like, I know, I'm sorry. It's just like that's the piece people forget. Okay, so yesterday I just said, like, use the sine and cosine and e to the x expansion. Okay, now we're going to go through, we're going to use this method, we're going to develop and find our sine and cosine. Okay, so here we go. So we are going to write the Taylor series. Actually, hold on. I'm going to show you because I need you to know some vocab, so I'm going to put something in there. Okay, so that's the vocab. I'm going to talk about what that's telling you in a second. Construct a sixth order Taylor polynomial. And the Taylor series that goes with it. That should be capital. Okay.
So they could easily reword that and say,
series for 5 sin x.
And then they don't have to include the x equals 0 case for you. All right. This, do you remember when we wrote the polynomial, and I only asked you to write the polynomial to x to the 4th, and I'm like, they have to tell you where to stop, like you don't get to just pick. When they tell you the order, that's telling you how many derivatives that you need to take, okay? So when they say 6th order, that is telling you to stop when you find your 6th derivative, okay? So if they ask you for a 4th order, you go to the 4th derivative. They will never ask you for a 10th order because we're not going to go to the 10th derivative, okay? There will be 3 Taylor series or Taylor polynomials that I will ask you to memorize because the AP expects you to have them memorized: sine, cosine, and e to the x, and those are on those need-to-know sheets that I gave you. Those will always show up on the need-to-know quizzes. So first let's learn how to generate them. So they're asking me for a 6th order. They are telling me the function sine of x. So what that means is I need the value for my function at 0, and then I need to go down I need to get all the way out to the 6th derivative, you guys. Okay, so when it says 6th order, that's how many derivatives I need to get to. And once I take the derivatives, I then need to evaluate them at x equals 0. Okay. All right, so we're going to generate this one together, and then I'm going to ask you to generate cosine on your own, so I want to make sure that you guys know what you're doing. All right, so f of 0 means you take 0 and you plug it into the original function. If I take 0 and I plug it into my original function, what do I get?
0.
0. Excellent. So that's 0. Okay, now I need to take the first derivative and then plug in 0. What is the derivative of sine?
Cosine.
Okay, so I'm going to write that it is cosine, and I'm evaluating at 0 what happens when I plug 0 into cosine.
1.
Okay. Repeat it and find those values. Then you take the derivative of cosine, plug it in. Then you take the derivative of that and plug it in. So keep repeating.
0, 1, 0, -1, 0, 1, 0, 2.
Sorry, but my question was, how can 2 factorial equal 2? Because
it's 2 times.
Oh, it's 2 times. Oh,
Because it's whatever that number is all the way down to
I've been sitting here trying to figure out, because I thought it was 2 plus 1, and I was like,
So it's that number multiplied all the way down.
yeah. I was just sitting there, it's like, man, yeah.
I would have said that too. Couldn't hear you, but just said it. I would have told you.
Derivative for cosine is negative sine, which you are back to 0. The derivative for negative sine is negative cosine. So you should have a negative 1. So you have 0, 1, 0, negative 1. You have 0, 1, and then 0. Is that what you guys have for your values? Okay, so now this is really important. My students stress out because it says 6th order, but when we write out our polynomial, because this is a 0, we're not going to have an x to the 6th. Okay? So when it says 6th order, it's not necessarily that you're going to have a 6th degree polynomial. It's that you had to take 6 derivatives. Okay, so make sure you know what that means, because that's the piece that kids will like forget. And they're like, oh, I forgot what it meant. So, and I'm like, okay, so know it for the test. Yeah.
But for f of 5, it's still like to the 5th, like
X to the 5th.
x to the
Yes. Okay, so now we're going to write. Okay, so now we're going to write out our Taylor polynomial. Okay, so we start out, it is our, so ready to remember, it's our 0th derivative over 0 factorial x to the 0, our first derivative over 1 factorial x to the first, our second derivative over 2 factorial x squared, wow, our Do you guys remember, like, you know where I'm going with this?
Yeah.
Plus dot dot dot. Okay, and we're gonna stop when we get to the 6. So we just need to plug in values now. Okay.
I don't know why this is so like.
I'm gonna show you visually what this does. I thought it was so, I never knew until I taught calculus what it was. I could do it, but I didn't know what it was doing. I'm like, that's so cool. It was like my complete nerd moment. So we're gonna do it visually in a second. Okay, so the value of my 0 derivative is 0, so this is gone. Yes?
This might be a dumb question, but what are we actually doing when we're doing like series stuff like this?
That's, I'm gonna show you visually what it is visually.
Yeah.
The polynomial that we write
Okay.
is going to be an approximation for this function. So when I, like
But approximating what? Just like a.
the graph.
Oh.
So then, what happens in your calculator, when it's trying to find sine of 0.1, well, it doesn't have value, all the values stored in the calculator. What it does is instead of sine, it has this long polynomial. It plugs 0.1 into that, and that's how your calculator is giving you the value for like sine and cosine and tangent is the polynomial approximation.
Okay. So I was just like, I didn't know what we're doing.
No, I didn't either. I'm telling you. That's why when I teach it, I'm going to do the visual. We're going to graph sine. We're going to graph our polynomial so that you see what it is. So we're taking something that like they couldn't have evaluated like old days.
Yeah.
They couldn't have evaluated, but they can evaluate regular polynomials like crazy.
Yeah.
So we're taking it and putting it into a polynomial that we can evaluate.
Interesting. All right. Now,
Interesting.
Who chooses
Kind
to
of.
do this?
So it's like the polynomial calculator, like
They have to go out, like we'll do a remainder theorem. This is like how many places you have to have it to a certain accuracy. Okay, so here we go. So that is gone. Your first derivative of the value was 1. 1 over 1 factorial is 1.
Wait,
So
why wouldn't it just be? Why wouldn't the value be 1? Because x to the 0.
X is 0, 0.
Because
Zero
x
over
is 0.
1. So
Why
it's
they
0.
all
but it's
say
times
that?
0.
Oh, never mind.
Okay,
you like
so my first derivative was 1 over 1 factorial is 1. So 1 times x to the first is just x.
Okay, so it's always going to be x. There's never going to be signs or e's within the.
Nope. And what I'm going to do is we're going to have this polynomial approximation.
Okay.
We're going to graph sine.
Yeah.
We're going to graph the polynomial approximation. We're going to see that it actually matches like really well right around x equals 0.
Got it.
The further out you go, the less it matches. But that's why you change your center is to match closer to the value they're asking you to approximate. Okay, so here we go. My second derivative is 0, so we don't have this. Okay, so now we're out here. My third derivative was a -1, so I'm going to put a minus. 1 over, and I'm going to leave the 3 factorial because we're going to have to write a formula to go with it. When we write our series, we write a couple of terms, a generic term and a summation notation. So I'm going to leave the factorial so that I can see my pattern. So my third derivative, 1 over, I'm going to leave that, and then x cubed. What happens with x to the 4th? It's gone. So now we're on to x to the 5th, so I need my 5th derivative, which is a 1, so I'm going to put a plus now. 1 over, what's on the bottom? Awesome.
That one.
Okay, now, when they ask you for a polynomial of that order, there is no dot, dot, dot. Okay? They told me they wanted me to stop at the 6th derivative. I stopped at the 6th derivative.
You're not gonna get the because it's just gonna cancel with the 0. That's what you were saying.
Okay, so now you guys, I need you to have out your calculator. I want you to visually understand we're taking stuff that they couldn't evaluate and writing it as a polynomial that they could evaluate. Okay, so in your calculator, I want you to graph, put into y1 sine of x, make sure you're in radians. For y2, plug in the polynomial approximation. So if you think of it that way, for me or for most of the kids, it tends to make a little bit more sense. Okay, so we're going to go onto the calculator. You have the stuff.
Or do I just have to do it for
I feel like I'm just gonna put 6.
Yeah.
It's in like math.
I'll just do 1 over 6.
Oh, this is
Yeah, that
going
seems
to really
like-
suck if this doesn't work.
It's 120.
Is it really?
Yeah.
Oh, that wasn't.
Oh, it does work. Okay, this is bad news.
That looks good.
What is that?
120.
actually is really good.
I think I messed up.
It
Oh,
starts
wasn't
out
mine.
up. It starts out up and down, but then it meets in the middle.
Oh.
Because we only went to 5.
Got it.
super cool.
It's a calculator, not beans.
I mean,
Cool.
Let's use it. Wow. That's impressive.
It's calculator, not
so can it only evaluate? Oh my gosh.
Look at it's like from those values.
It's a calculator, not beans.
Why is it
cool? That you're gonna
That
take
screen
this.
looks funny. Look at it.
Yeah, no,
Okay.
it's
Fine.
Mine was no.
no, like hers
It's
is
dark.
Yeah.
You just got to
Wait, so Prior, how does it evaluate
understand.
numbers that are past like
Yeah,
the?
it's so that you can't evaluate directly.
Hold on, this is
Why
like.
is that?
Right?
Oh, no. Okay.
This is the
Don't talk to me because this is like barely hanging on by like its last little leg.
Oh.
whole reason my friend is
So that if I put 0.1, if you're trying to evaluate 1, if I put 0.1,
It's really pretty
Yeah.
perfect.
there's no way to
Maybe
figure it
I understand.
That's it's really perfect.
Okay, you guys, I graphed mine from negative 2 pi to positive 2 pi. Okay, so that's the window that I used, was I graphed from negative 2 pi to positive 2 pi. We only have 3 terms in that polynomial, and honestly, it's not bad. From, I don't know, maybe like negative pi to positive pi, it's like fairly close. What can we do to make it more accurate?
Go out to more.
Go out to more degrees. Okay, so go back into,
Oh man.
so instead of stopping,
Okay.
yes, cool.
Mine only connects in the very middle. It doesn't have that
What's your window?
curve around. It's the same as yours.
Are you in radians?
I press
Bad.
please.
Bad.
I get like
Oh, I get it.
nine.
So you would skip the 6.
And it'd be a negative for the 7.
Okay, so you guys, what's your next term?
Negative 1/7.
Negative. Okay, so include your subtraction. X to the 7th. Over. Alright, so I think it's in math.
Wait, is it? Oh, it's one.
You guys, when you go into math, number 7 is probability. You should find a factorial down in probability is your factorial.
Where's math? five. What? Oh, yep.
Above your 5 in yellow.
And what is it?
What's the
Statistics.
probability?
Those are still fun.
Yeah, it's probability.
Okay.
Oh.
Oh, 7.
You could just do it after.
Oh.
And you guys, honestly, I'm going to go in and I'm going to put the next term in also. So I'm going to do plus an x to the 9th over 9 factorial.
It's under probability.
Math is the yellow above 5, so you do second 5.
Ours is
And then
blue.
number 7 is, okay. And then you do second. Okay, so I'm going to do 2 more terms. Okay, and now when you graph it,
What was your window again? You were going from.
I did negative 2 pi to positive 2 pi.
Okay.
Oh, it's like.
Oh,
So
wow.
math and number 7 is probability. It's really not bad to a certain degree, but now, we just talked about Maclaurin is always centered at x equals 0. Okay? Taylor series can be centered anywhere. So what you can do is if you are way out at like 10, you don't want to start at 0 and have to add a whole bunch. Wouldn't it be just easier to center it out at x? Like if you want 10.2, then center it at 10. Write the polynomial and then evaluate there. So that's why they have where you can change the center. Otherwise, you could be here forever. Like if you're way out at 100, think of how many terms you're going to have to add. So if they want you to find like sine of 100.2, you would generate your polynomial out at 100, and then you would plug in the 100.2 to approximate values. Okay, so the reason why they have the center, at the center, it will be almost an identical match with only a few terms. Instead of having, now you can keep adding terms, you can sit there until you can get it to match all the way out from negative 2 pi to positive 2 pi. But then if you move out any further, then it peels off again at some point. It's not going to be a perfect match.
I'm confused as to what you were just saying with the centuring.
Well, like if I want you to find sine of 100.2, You don't want to start at 0 and keep adding enough terms until it's
So you
accurate
do
way
like-
out to 100.
Parentheses X
So
minus
then
100.
back here,
Yeah.
and this is what we're going to do. We're going to move our center in a second.
Okay.
Oh, my
So
goodness
instead
gracious,
of
now it's-
centering it at 0, if I want you to evaluate at 100.2, center it at 100. And then, so now you guys, this polynomial approximation, so now watch, this is what the next thing we're going to do on the calculator. I want you to find the value. I would center it at x equals 0. Find the value for sine of 0.1 and evaluate your polynomial approximation at 0.1.
Oh.
Okay, so find sine of 0.1 and then evaluate your polynomial approximation at 0.1. Okay, because it was centered at x equals 0, this polynomial approximation should be wickedly close to the actual value because I'm telling you this is approximating my sine graph really close to the center.
You mean we're plugging this in our calculator?
Yes.
Oh, okay. I thought you were trying to make us do this.
Yes. Nope. And I'm holding on for dear life to this, and then I need to order a new cord because it's really sad.
Is it like your phone charger? You know, if you like bend your phone charger enough, like you
Do
have
you
to hold
like?
it?
I've got a
Yeah.
death grip on this to like prop the back up. So my sine of 0.1 is 0.0998 blah 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 blah. And now I need to type in. I'm just doing the polynomial that they asked me to.
Wow. Whoa, they're like perfect.
I can't read. Oh my gosh.
Oh wow, yeah.
Whoa, way out here.
I mean,
go
that's
farther, then it's not.
so minimal.
It is why because you guys you have to remember like
Yeah,
calculus
I
was
want.
developed before
Oh,
calculators.
you went to that one. I went to the 9 and it was perfect.
Yeah, mine came out perfect.
Oh, I
Okay,
didn't go to
no,
that.
I
was
only
real
did the
quick.
polynomial that they asked me to write.
Okay.
So I did the others just so you could visually see the more terms, the more accurately it would represent it. Okay, so it's not that you have to understand what it's doing, but it's actually kind of nice to know what it is you're doing. If you totally are like, I have no idea, but I'm sure I can take derivatives and put it over factorials, you'll pass. It's just nice to actually know like, oh, that's in a nerdy way kind of cool. Okay. So, yeah, that was. Okay, so now, yesterday, I gave you, and I just said use sine, use cosine, use the e to the x. Okay, for this sine, we're not going to write the Taylor series. Taylor series is a couple of specific terms, the general equation, and then summation notation. So when they ask you for a polynomial, the polynomial stops wherever they told me to stop. When they ask you for a Taylor series, 3 pieces have to be included, and you want to hear what these 3 pieces are because if you don't include one of them, the AP test will not give you credit for writing the series. Okay? If you only have 2 of the 3, they will not give you credit. So the 3 pieces to write a series, a couple of specific, the general formula, and then equals, and in summation notation, the general formula with care being taken, 0 versus 1, if you guys remember what I'm talking about, like where you start. Okay, so now back over here, I need to write my Taylor series. So I wrote my polynomial, and the polynomial is helpful because I needed a couple of specific terms anyway. So for my Taylor series, I have a couple of specific.
So this is the first part?
So for Taylor series, you need a couple of specific. Then we're going to write the general equation. Then we will write it in summation notation. Those are the 3 pieces you have to have. So I wrote a couple of specific. Okay, so there are some things that like will reoccur. So when you see it from now on, you'll be like, oh yeah, I've got this. For it to alternate signs, it goes minus and then plus and then minus and then plus and so on. For it to alternate signs,
What's that little dash in front of the
it's that you're alternating signs. So this was a plus, so then I have like a minus. The next one's a plus. Dot dot dot.
If we don't write that on the
Could you just do minus dot 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 plus?
Okay.
If you want to start the other way, so this one, it works that the first one's positive, second one's negative, right? If you want it to be the opposite, you want it to be negative then positive, Do you do just n plus 1? Or n
You
minus-
can. You're going to have to play around with the exponent or your starting point.
Okay, that's what I was wondering.
Okay, so -1 to the end. This will allow it to alternate. And you guys, the question of what if it starts with a negative or what if my sign isn't matching? This might be an n, it might be an n plus 1. You will have to play around with this.
Where did you get the -1?
Because I need it to alternate, and the only way to make it alternate is to raise a negative number to an even power, and then a negative number to an odd power, and a negative number to an even, and a negative to an odd. All I'm doing this is only taking care of alternating.
Yeah, but if they're alternating like the 1 over, like they're both odd powers there, and they're alternating.
Because there's a negative to an
We're
odd
getting
and
there.
an even to
Oh.
Totally getting there.
Okay.
Okay, here we go. Over. What's always on the bottom?
In fact,
It's not just n factorial. They are always odd. Okay, so flashback. Oh, how do I make something even? So if I tell you x is 3, how do I make that even?
you add one.
times with 2.
Or what if it already starts even and I need to guarantee that it's even? You can still multiply by 2. So if you have to create even exponents or even numbers, once you see it once, you're like, okay, I just know to do that. I'm not expecting that you were going to do that in the beginning. How do I force them to be odd?
Minus 1.
You can either -1 or you can add 1, and I don't care which one you do. All it's going to change is your starting point.
So is it n minus 1 factorial?
I, in all honesty, because I mess up negative signs,
Okay.
so
Oh.
but it's a personal preference. It's not that it's wrong.
Oh,
I just mess up negative signs, and I don't mess up positive signs. So I'm going to, so this forced it to be even,
yeah.
okay?
So once it's even, as if you add.
And then once it's even, if you add 1, it's guaranteed to be odd. Okay, so now that you have this little piece, these are odds and these are odds. So instead of just n factorial,
It's
2n plus. Oh my god.
and then your x is, exponent was always odd. So again, whatever you used here, if you use 2n minus 1 here, you have to use 2n minus 1 here. So whatever you chose down here, it has to match. Okay, and so for Taylor's series, we wrote a couple of specific, we wrote the general, so now plus ... equals, and now
I'm just wondering, why does the book always the way that they do notation in there is they always take that summation and like put it underneath. Is there a reason they just
they might run out of room. I have no idea. So whatever you wrote for your general goes in here. So once you've written that, that's the hard part. You know it's infinity. We need to know where to start. If you did the +1, it's at 0. If you did the -1, it's at 1. Okay, because if I plug in 0 to here, it makes my exponent next to the first, which is what I started with. It makes it a 1 factorial. And -1 to the 0 is 1. Okay, now I'm going to check. I always check the first couple because I'm always leery. Do I need to do something with this? So now if I plug in 1, -1 to the first is now negative. 2 times 1 is 2, plus 1 is 3. I've got my x cubed. So I've got my 3 factorial. I'm going to mentally check when I plug in a 2. Negative 1 squared is positive, and my next term was positive. 2 times 2 is 4 plus 1 is 5 over the 5 factorial. So however many of these I've written, I check and plug it in to make sure it's right, just because it's like they're easy points, and if I left off a little piece, I want to be able to fix it. Okay. Sine graph. Just watch. Cosine graph. Sine graph. Is it even or odd? Sine graph.
Even.
Even has symmetry with respect to the y-axis. Odd has symmetry with respect to the origin. Odd.
Oh.
When we did even and odd functions last year, this is odd. Look at the exponents.
Wait, which were we just looking
I
at?
thought we were talking about the bottom.
I thought we were talking about the bottom one.
Well, that's the cosine graph, and I'm asking you about the sine graph.
Okay.
My sine graph is odd. Please notice that its exponents are odd.
Oh my god.
Okay. Your cosine graph is even,
So the exponents are gonna be.
and it is very nice. When we write it out, its exponents are even. Please notice, this is like the piece that people, like they're little things.
Oh.
This sign is a plus, it alternates plus, minus, and so on. So the actual first sign that you write is a negative when you write out your sign expansion. Okay, so now what I'm going to ask you to do is start over and write cosine. I want you to make sure you guys know how to generate this stuff.
Are we going to the 6?
So we're going to literally do the exact same problem, but with cosine first. And we're going to do the polynomial and the series.
What do you think the hardest part of is for this whole chapter?
Keeping everything straight. So the exact same problem, but with cosine instead of sine. When you think you have it, check in your group, and once you have a couple of the specific, and you've written your full 6th order, when you write the series, pay attention to the even and odd, how to write them.
So the only difference between the polynomial and the series is that the series adds on the summation.
The polynomial stops, however many places they told you to go, that's all you write. And then the series is you're going to need a generic and then a summation.
Yeah.
Is it still called a Maclaurin series?
Maclaurin.
Maclaurin series?
They just ask you to write the Maclaurin series. They don't have to say at x equals.
I was just wondering because you also had, I thought it was called
Maclaurin.
Maclaurin polynomial. I was making sure it was also the series also applied to these rules.
For that first term, would you just write 1 or would you write 1 over 1?
I don't understand.
Well, if you write 1 over, it would be 1 over 0 factorial x to the 0. So just write 1.
Okay.
I'm just curious. I don't know why, but like the first one is 1 because it's like
it's always
either
the
that
derivative
is always
says,
okay. I understand now.
One of the ones.
Oh, is that the same thing? Wait, okay, hold on.
But I mean the general form.
Yeah, that's the general form.
Like when
F over M of A, well, the one that we're always gonna have is 1 or negative. So it's the negative one of the. Like, see, okay, look at the general formula she gave us when it starts at 0.
Yeah.
Check, you guys.
after you come here, I don't understand how to do the other part. Like generate the thing.
Well, it alternates, so you're gonna have to have a negative 1 to the n, or a negative 1 to the n plus 1. You've got all even, so what are you gonna do for evens?
2n?
Would it be wrong to write like the whole A not like every single time? I don't know why like.
Totally don't care. Okay, so check, you guys. These also alternate signs. Cosine is an even function. Its exponents are all even. So this is my 6th order Taylor polynomial. While it is 6th order, this one has an x to the 6th. The sign was the 6th order and did not have an x to the 6th. So please don't let that part freak you out. Just know that you went to the proper derivative and stopped. Okay, so I'm going to, from here, I'm going to put like plus dot 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 so I don't have to rewrite the whole thing, but know that this is my answer to the polynomial. So I'm going to put plus dot dot dot. So you're generic. To alternate, what do you do to make it alternate? Okay, so put that in. And it may have to be n plus 1. We're going to have to play with that once we actually like get to our summation when I'm plugging in values.
Wait, why would it have to be n plus 1?
Just depending on, you will generate some where like it starts with a negative. So if you're starting with 0, it wouldn't start with a negative. So you would have to have like an n plus 1, so then it was to the first, so then it was a negative.
Okay.
So it just depends on the
So
particular
if it
series.
starts with a negative, you'd have to, okay.
So I just want you guys to know, first, this is like general, this is where it starts, but this may need to tweak a little bit.
Change the front one.
Why on this one is it not minus plus minus plus?
You can, hon, I'm just trying to get through this because we've got like 2 more examples and we have a half an hour left. These are all even. So on the bottom, please make sure the parentheses are very important. If you fail to do the parentheses, the n is the only thing factorial, and then your whole answer would get multiplied by 2. Factorial for order of operation happens before multiplication. So to make it the entire quantity, you have to have parentheses. The exponent was the same, and it was also even. For your summation, I'm going to put this in, and then I have to decide where to start. This is what I'm going to tell you when I ask you to memorize sine, cosine, and e to the x. Your life will be a million times easier if instead of just memorizing the first couple of terms, you also memorize or like are fairly familiar with the generic so that you do not have to sit and recreate this every single time. It will be very time consuming on the AP test if you have to recreate this every time and if you have to recreate this every time because they're primarily going to ask you to modify. They're going to ask you to do like the homework problems that I gave you last night, but without actually telling you the series. So these are series you're supposed to just know off the top of your head.
So that's why we had to flip back because we didn't know.
Because we
It's
didn't
really
know
not
that.
that hard to memorize. If you just memorize the
Sine's
2n.
odd,
Yeah,
cosine's even.
it's not hard at all.
So, at any rate, infinity. Where am I starting?
0.
Okay. X to the 0. Yes. Okay. All right. So now, you guys, I want to show you something that I think is totally nerdy and super cool. Somebody read me our sine polynomial.
X minus x to the 3rd over 3 factorial plus x to the 5th over the 5th factorial.
And that was my sine. And if I needed to add one more, I would have had that. Okay.
Oh my god, if You put them together. It's 1 plus x plus. Oh my gosh.
Yesterday, we did modifying. We had substitution, we had multiplication, division, or we had addition, subtraction, and then in a totally separate category we had calculus. How do I get from calculus, from sine to cosine?
Derivative.
It's radioactive. What's the derivative for x?
Stop.
Oh my gosh.
Stop. Okay, the derivative here becomes 3x squared over 3 factorial.
Oh, what's the 3's cancel us? Oh my god, I can't do this.
Okay.
Is this ever gonna have any relevance, or are you just doing this to mess with us?
Well, because then when you're trying to memorize and you're trying to debate which one's which,
Oh my
if
god,
you
if
know
you
one,
know that
you
it's
know
a
the other. So
Ah!
that's what I'm trying to
Does
get
it
you
work
to see.
the other way around?
Well, okay, but if you want
No,
to
you're right.
integrate, no, you could
You
integrate
can integrate
Oh,
without
and then the
No,
negative
no, but I
with
mean
it.
like if you
So I make a point, like I always know the derivative of sine is cosine, and then I kind of like think about my stuff. So if I know my sine, I for sure
Wait,
can get
no,
to
you could. I mean,
cosine.
I meant like if you took the derivative of cosine and then multiplied it by negative, it works. Oh my gosh.
Does that work with the
Oh,
summations though?
forever. I hate it.
Wait.
Hurts.
Okay, so when you're like, oh my gosh, okay, I've got to memorize this stuff, and I've got like completely bizarre, they're related still. All the stuff that we did yesterday actually comes into play, and like the weird, like, oh, that would actually make my life a little bit easier. So if I write one and I write the other, I have a way to check my work, because you guys are actually really good. And once you get like the first two, you'll be like, oh yeah, I remember.
I'm gonna start crying during this test.
Yes.
Does this also work with the summation, or do you have to do those separately beforehand?
If you go back and you do your derivative, it will work, because you would have the exponent comes in front, and then you subtract 1. And do you remember when you said it was 2n minus 1? And I'm like, you can do 2n minus 1. I prefer plus 1, because I do not like to have minuses. Okay, so you guys, this question is, does it work for the summation or like the generic? I'm going to leave off the -1 piece. So this was, I wrote it as x to the 2n plus 1 over 2n plus 1 factorial.
Oh my god.
Derivative. Where does this go?
2n plus 1 minus 1.
2n plus 1. X to the, when I subtract 1.
It's 2n.
Okay, now look. Here, when I wrote 5 factorial, it was 5, 4, 3, 2, 1, and so on. So 2n plus 1 factorial is 2n plus 1. And then what's my next term?
2n.
2n, and then 2n minus 1 and 2n
So it's
minus 2 and so on.
factorial.
So this is,
wait, what?
Yeah, it's 2n factorial.
because what?
Because it's 2n and then the 2n plus 1.
So here, when I go down by 1, it's 2n. Then when I go down by 1, it's 2n minus 1.
Why would you go down?
Because you're
Because now I need to have you see that those cancel, and gives me.
No, it's because you're writing the derivative.
Oh.
So yes, it works too. So yesterday when we modified, and I told you, modify the general because it makes your life easier. All the stuff that we did yesterday works. We're just learning like where this came from and how if they give me something else, I can fix it. Okay, so as far as modifying goes, you need to make like this super important in your head because my kids always miss this, and I'm like, no. You can take the series that they gave you in the book. They are Maclaurin series. They are all centered at x equals 0. Any series that's based on the sine, the cosine, the e, where they are also centered at 0, modify the crap out of those. Don't generate them. If they are not centered at 0, you have to start all over and do old-fashioned by hand. You cannot modify Maclaurin centered at x equals 0 for values that are not at 0. Okay, so what I mean by that is, if they ask you to generate, whatever, the 6th order polynomial for sine of 2x at x equals, I don't know, 7 pi over 6. You cannot just go to your sine series and plug in 2 x's. Okay? Because those values for the coefficient came from the derivatives evaluated at x equals 0, and now my derivatives would need to be evaluated at 7 pi over 6, which are very different values.
Is this what you were talking about with the x minus a? Like you.
Yep, I'm going to do one with the x minus a. But I wanted to show you, so you need to memorize sine, You need to memorize cosine. E to the x is easy. They are all pluses and it goes up. So the e to the x is very easy to memorize. Those three, I will ask you specifically. Okay, so now let's do centered somewhere else. I know it's long, you guys. Let's do e to the x because those derivatives are just the nicest ever. So let's make an e to the x not centered at 0 because they are happy. So we did sine, we did cosine. A reminder, so your Maclaurin series, we did it yesterday for e to the x. Your Maclaurin series is the e to the x. Okay, so we did it yesterday. Okay, your Maclaurin series, it's kind of those put together, but no minuses. Okay, so kind of if you combined sine and cosine, and you made them all positive, you would have your e to the x. So you have the 1, you have the x, you have the x squared over 2 factorial, you have the x cubed over 3 factorial.
Oh, now I get what you're saying.
Okay, so for me, like when I think of e to the x, when I have to memorize it, it's kind of sine and cosine put together, but all positive. Okay, so it has all the evens, it has all of the odds, and it's got the pluses. Your generic, you guys, there's no alternating, so there's no -1. You've got an x to the n and n factorial. Okay, so now I'm going to ask you, though, I swear it's the last problem. I know today was long. Find the Taylor series. So I'm asking you for a Taylor series. So I didn't ask you for a polynomial, so I didn't tell you how many derivatives to take. So you need to take enough until you can see a pattern so that you can write a general and you can write summation. I typically do, like the first 3, maybe 4, should give me enough to write it. Okay. Why can I not take this and modify? Because it's not centered at 0, because once you do this, I'm going to ask you to do it for e to the 2x centered at x equals 2. Okay, so if it's not at 0, you can't modify somewhere else. So generate your series.
Okay.
Yeah, that's why we're doing this one. It should be super fast. That's why we're doing this, is because it's going to be crazy fast.
Sweet. This is correct.
Yes.
So,
We're going back to school. But you do F
You always have to start with that.
or is it F
That's why, but if it's not at 0, you can't plug in 0. You can plug in whatever number we're centered at.
So for the generic, I'm confused.
Series goes with
So I'm going to go out to like the third derivative because that should give me 4 terms. So I'm going to do f, f prime, f double prime, and f triple prime. So that should give me 4 terms. That definitely should give me enough to see the pattern. But when I do these, Maddie's question is, am I still plugging in 0? No. You're plugging in 2. And when I write my formula, it's not just going to be x to the power, it's going to be x minus 2 to the power. Okay, so when you're not centered at 0, zeros don't come in.
I feel like it's always.
The derivative for e to the x is always e to the x. So I gave you like a super nice.
I didn't want to write it down until I knew I was writing.
Yeah, I was like, oh, then I'll just e squared. Alright.
Woohoo! It is not usually the case, but that's why I gave you e so we can kind of pick up the pace. So write out your first couple of terms, write your generic, and then put it in summation notation.
We forgot the second
to
one.
the third.
That one.
Is it just e to the 2?
Yeah, it certainly is, Miriam.
Oh, shoot.
to the
Don't forget your x minus a. Even the answer book forgets it on a couple of them, you guys.
Oh wait. Oh, so when you plug in the x's of every single thing, that's
It's a joke. The same. E to the same. It's the power.
oh. Dang it.
That's what I thought. That's what I thought we were doing. I was getting so glad.
Okay, so remember, you guys, I'm going to scroll back a while. Okay, when it is centered at x equals a, the derivatives are evaluated at that value. It's still over whatever factorial, but when you write your x, it's x minus the center. Okay, so that's why I have x minus 2 in all of those parentheses, is because it was centered at x equals 2.
So could you just put for your general one e squared over n factorial? Because it's always going to be the
X minus 2.
yeah x minus 2
Yes.
then.
Yes.
How come the first e to the 2 doesn't have the x minus 2 with it?
You could put it, but you need to put it as an
Oh,
x
to the-
minus 2
okay.
to the 0.
Okay.
So the first term's always a constant unless that derivative was 0.
Okay.
Oh wait, so did we start at 2?
I don't think so.
I started at 0?
You started at 0.
You started 2.
No, you
I
started.
don't think so.
You started.
Because it's
Zero.
0.
So because anything with the 0 is 1, so then it's e squared over 1.
This has nothing to do with the center. This has to do what I'm plugging in for the ends
Okay.
to give me my general
That's what I
terms.
thought.
I think that's what I was getting confused about before. I was just like,
Okay.
the whole nx.
Are you gonna like me by asking me to do an example where it's not really hard?
Where it's not really hard.
Like,
This
or
one
I mean,
wasn't
it's not
really hard.
where it's not really easy.
20 minutes left.
I'm just going to
It's
get you
not
on
like
homework
negative
or
or
not.
Okay, you guys make mental notes. Make like big notes in where you have written this. You will even find that your answer book will have x, x squared, and x cubed. Okay, so please make sure you guys will remember to evaluate at that other value. That typically is not the error. Typically the error is that you forget to include it in your parentheses. Okay, and please remember that these are factorials and not just regular numbers. Okay, so I asked you for a Taylor series, so we have a couple of terms so I can see a pattern. I wrote the generic, and then I put the generic in summation notation so I knew where to start to generate that specific polynomial. Okay, today's stuff goes back to that page. Now they'll ask you to generate your own. Okay, so they'll ask you to do like I did with e to the x centered at x equals 2 and whatnot. Okay, so they're actually going to go back. If they're still just asking you to modify and it's centered at x equals 0, pull out what you did yesterday and keep modifying. Make sure you memorize before we take the quiz next week, sine, cosine, and e to the x. Okay, make sure you know their polynomial expansions.
We only
So
need to
any
know this.
specific degree or
Those are the only 3 that I asked you to for sure memorize.
no,